Hello, and thank you for joining us. I am Jasmine Navarez, Digital Content Coordinator at Simulations Plus. I'll be hosting today's webinar behind the scenes, making sure we don't have any technical difficulties. In this webinar, Drs. David Miller, Vice President of ADMET Cheminformatics, and Michael Lawless, Senior Principal Scientist of Cheminformatics Solutions, will walk you through the latest version of the ADMET Predictor software, showing you how to begin leveraging the new and expanded functionality to drive your pipelines forward. Our Business Development Director, Tom Sanderson, will serve as your moderator today. A few housekeeping items before we begin. We take your privacy rights seriously. By registering for and attending this event or participating in the Q&A session, you are allowing us to contact you for follow-up. You may ask questions via the questions panel on your dashboard. I'm sorry, before we start, we're going to conduct a short poll to better understand your familiarity with ADMET Predictor. So the first question is, are you currently a user of ADMET Predictor? And if you are a user, what modules of ADMET Predictor do you use? And there's a couple of answers to choose from. So I'll give everybody a couple seconds here. All right, so I'll go ahead and end it there. So it looks like almost 50-50. There's some that are not users and there's some that are. And then for the top models used, the number one was AIDD. I'll now pass it over to Tom to introduce our speaker.
Thanks, Jasmine. Welcome, everyone. I'm pleased to introduce our presenters today, David Miller and Michael Lawless. As Jasmine's mentioned, David is our Vice President of ADMET Cheminformatics Solutions at Simulations Plus, and Michael is our Senior Principal Scientist of Cheminformatics Solutions. David started his career studying physics at Stanford University, followed by his PhD in biophysics at the University of California in San Francisco. After his studies, he worked at CombiChem, then BioReason, and later Sage Informatics, which was a small cheminformatics software startup that was acquired by Simulations Plus in 2005, where he's been since. Michael studied his chemistry at Missouri State University before undertaking his PhD in physical chemistry at the University of Arkansas. He later undertook a postdoc at the University of Texas at Arlington before working at Tripios. Michael joined Simulations Plus in 2011 and was first lead scientist on a cyclooxygenase NCE project, and then later collaborations with the FDA and NIEHS. More recently, Michael is one of the developers of ADMET Predictor, working on new predictive models and more. Both are very well placed to present our webinar today, describing ADMET Predictor version 13, and I'll hand over to them. Thank you.
Great. Thank you very much, Tom. I'm going to turn my camera off so I can focus on the slides. So welcome everyone to today's webinar. We have quite a bit to cover today, so I'm going to jump right in, but I have a few introductory slides for the benefit of those who may be new to the ADMET Predictor platform. So ADMET Predictor has 4 main sets of functionality. The most well-known is property prediction. As of this version 13 release, I believe we have something like 220 predicted properties in the software across the categories listed here. So there's PhysChem, transporters, metabolism, toxicity. In the last commercial release, we introduced the DILISIM module, which focuses on drug-induced liver injury. And then there are several user customizable risk scores across several ADMET categories. The pharmacokinetic simulations module we call HT-PBPK. You can estimate a number of PK parameters like fraction absorbed and bioavailable, estimate plasma concentration time curves. The optimal dose feature lets you estimate the dose that would be required to achieve a certain plasma concentration. The last commercial release introduced estimates of tissue partition coefficients, or KP values, and there is a parameter sensitivity analysis feature as well. The model building engine is what we use to build the commercial models, and clients can use that same engine to build models using their own data. It comes with our molecular and atomic descriptors, supports several modeling methods, both regression and classification type. Uncertainty estimates are provided for regression models and confidence estimates for classification models. And then it has a technology built in that we call delta models that in essence lets clients extend our models into their own chemical space. I'll talk a little more about this later on. And then finally, there are a number of cheminformatics features, one of which is a new module called AIDD, focused on compound design. And we've made quite a few changes here that I'll talk about. Just a few comments on deployment, because I'll talk about several of these later. There's a graphical desktop version that is currently limited to the Windows operating system. But the command line version, which has essentially all of the key ADMET Predictor functionality, it runs on both Windows and Linux. We have components for both KNIME and Pipeline Pilot. Recently, we introduced a REST API. So this is a client-server model where the server is deployed at the client site as opposed to at Simulations Plus. The REST API makes it quite straightforward to integrate ADMET Predictor functionality into your informatics infrastructure, whether it be a third-party software tool or something that you have built yourself. In the last commercial release, version 12, we introduced a Python module called PyADMET Predictor. It serves as a wrapper around either the command line or the REST API. It has lots of examples, both ADMET property prediction, HT-PBPK simulations, and lots of other functionality. We ship this with the ADMET Predictor software, and it's also available through PyPI, so you can install it using pip. We'll talk quite a bit about both models and HT-PBPK simulations. So I just have a brief methodology slide for both. So our predictive models are what you would call typical QSAR models. So they begin with data that we gather from one or more of these sources. We calculate our molecular and atomic descriptors, and then build collections or ensembles of machine learning models. In the past, these have traditionally been neural network models, although for this release, we did explore an alternative method that I'll talk about later. The average predictions from the ensemble then form the final model. And this is one example model, our PKA model. We rebuilt this for version 11 of the software. And then last year, in 2024, this model took first place in the Eurosample PKA prediction challenge. So truly a best-in-class model. Our user manual has the similar kinds of performance plots for all of the models that we have in the software. The pharmacokinetic simulations are different in that they are not machine learning models, but rather mechanistic simulations. The underlying system consists of the ACAT model to describe transit through the GI tract, and that is coupled with a compartmental model to describe the distribution and elimination. The system does require inputs. So physiological parameters would be things like the sizes and pH values of individual compartments here. These are taken directly from our flagship GastroPlus software, the full sort of expert, PK simulation software package. Formulation parameters would be things like dose, particle size, and so on. Compound-specific parameters, things like solubility, permeability, and so on. Running the simulation involves integrating a series of differential equations, and then from that you can extract PK endpoints, plasma concentration profiles, and so on. Okay, so with that very, very brief introduction, I'll start talking about the new features in version 13, starting with the PK simulations. So the first enhancement was to add 2 new species, dog and monkey, to the 3 existing ones, which were human, rat, and mouse. So now in the user interface, you have them arranged in more of a drop-down style. Along with the new physiologies, we've added 6 new species-specific property models to serve as inputs to the simulation. So 2 models for fraction unbound in plasma, and then 4 for intrinsic clearance, either liver microsome or hepatocyte. So now, if you choose in the user interface a species, these new models will appear as the defaults to use as the inputs to the simulation. Of course, you're not required to use our models as the inputs. If you have in vitro experimental data, you can use that. You can even use your own models. For this release, we were not able to develop models for ratio of blood to plasma in dog and monkey. We could not collect enough data, but that's something that we're continuing to work on, and we hope to have those models in a future release. This shows the current performance plots for the 6 new species-specific models that we did add for this release. You can consult the user manual to see the sources of the data and so on. Sizes of the data sets vary quite a bit. Some were on the small side, but the performances were pretty good. And again, this is something that we will continue to augment as time goes on, as we find new data. And this just shows a comparison between ADMET Predictor and GastroPlus, focusing on dog and monkey, and 3 properties: fraction absorbed, bioavailable, and area under the plasma concentration time curve. This is for 100 randomly selected FDA drugs. And you can see that Predictor and GastroPlus give virtually identical predictions. This is not wholly unexpected. I mentioned, we take physiological parameters from GastroPlus to use in ADMET Predictor. But as I've mentioned before, there are some differences in the way simulations are implemented in Predictor versus GastroPlus. Slightly different way of handling precipitation, for example. But these differences are usually very, very small, as you can see here. We did a similar comparison of many, many CP time profiles as well, and found similar levels of agreement. Okay, the second big enhancement to HT-PBPK was to the time series display. So now, in addition to displaying plasma concentration versus time, you can also display amounts dissolved, absorbed, and bioavailable. So this brings ADMET Predictor more in line with the functionality of GastroPlus itself. It's quite useful in being able to see things like whether or not absorption is limited by dissolution, whether there's evidence of precipitation, as shown here, and so on. In the user interface, which is shown here, there are 3 new buttons where you can toggle between, just the original plasma concentration display, just the new curves, or the combination of the 4, which is what we call a Bolger plot in honor of Mike Bolger. In addition to generating these curves in the graphical user interface, you can also create them using either the command line or the REST API. And then finally, in HT-PBPK, we've enhanced the parameter sensitivity analysis feature. So we've had this functionality in ADMET Predictor, but you were limited to looking at only solubility or permeability as the inputs. So we've now expanded that to include all the major HT-PBPK inputs, things like log P, FUP, clearance, even dose. So again, this kind of brings the ADMET Predictor functionality more in line with what you see in the GastroPlus interface. And again, you can use this functionality not just from the GUI, but also the command line and REST API. And in these two, you're able to perform the analysis on more than one compound at one time. In the graphical user interface, you're still limited to one at a time. Okay, so those are some of the enhancements to HT-PBPK. We're going to move on to models now. We've made a number of changes here. One of the most significant was to our model of aqueous solubility. So up until now, our solubility model has been based on native thermodynamic solubility. So native refers to pure compound dissolved in pure water. We've had just about 3,400 values from a major paper from Malin and the Aquasol database. Now, last year, Alex Avdeev published a book predicting solubility of new drugs that contained a large number, almost 3,500, intrinsic solubilities. Intrinsic solubility refers to the solubility of the neutral species. We made the decision to convert our original data set into intrinsic solubility so that it could be combined with the data from this book. So after doing that combination and duplicate removal and curation, we have a data set that's almost 4,900 compounds. So significantly bigger than where we started. With that new data, we built a model of intrinsic solubility. There are both 2D and 3D flavors. So this is the kind of the default model. This is the one that incorporates 3D descriptors as well, and that requires 3D structures to run. Then with that new model of intrinsic solubility, in combination with our own pKa model, we re-derived the 4 dependent models. So the native solubility that up to now has been the primary model, the base model, native pH at saturation, solubility at a user-specified pH, and the solubility factor, which is the ratio of salt solubility to intrinsic. So these 5 models, we've had these 5 models before. We just made the decision to train them in a different way, and the result is a larger training set and better overall predictive performance. The same book from Alex Avdeev contained a large number, almost 3,500 melting point measurements, which we used to build a new model of melting point. This, as we expected, turned out to be a dominant descriptor in the new intrinsic solubility model, along with S plus log P. So this new model is available. One of the activities that we undertook in the last release cycle was to explore alternative modeling methods. And one that turned out to be the most promising was the so-called XGBoost method, which is from the family of extreme gradient boosting algorithms. We looked at many of our existing training sets to see whether XGBoost could enhance the performance, and found 2 models in particular for which that was true. One was volume of distribution, the other rat acute toxicity. So without changing the training sets themselves, we simply rebuilt those models using XGBoost. I don't have side-by-side comparisons of version 12 versus version 13, but you can do that comparison yourself. The improvement in performance was significant in both cases. We had hoped to make XGBoost a formal modeling method within our ADMET Modeler software. We were not able to do it for this release, but it's something we think we can do in the near future. And then finally, in terms of new models, we have 5 new rodent acute toxicity models. These are based on data that we extracted from ToxValDB from the EPA. They are for mouse, rabbit, and guinea pig oral toxicity, rabbit dermal, and rat inhalation. We used a variety of different modeling techniques here. So one was XGBoost, one was traditional neural networks, and then 3 used the delta model approach that I referenced earlier with the rat acute toxicity model as the reference. I just want to have one more slide to further illustrate how this works. And this is using the guinea pig acute toxicity model as the example. So here on the left, it's the predicted and observed plot, but here the predictions come from the reference model, which again is the rat acute toxicity model. So the predictive performance is actually already pretty decent. So clearly there's a correlation between the rat acute toxicity and the guinea pig. In the delta model approach, we build a model on the predictive errors from the reference model. And then the combination of the reference model and the error model give the final delta model. And you can see the final performance, and actually judging from the statistics, it's significantly better than the reference model by itself. Again, this delta model technology is available within the ADMET Modeler package. Okay, jumping to a few enhancements in the ADMET Predictor user interface. We've added a new column with a spreadsheet column with so-called PK50 values. So those values are midpoints of the ASP curves, which I'll talk about in a second, and as such represent the true acidity or basicity of individual functional groups. So this plot comes from our pKa microstates display. So it's showing for the 3 ionizable groups of this compound, the carboxylic acid and the 2 basic nitrogens. What is the fraction protonation as a function of pH? And the red dots are the midpoint of those curves and define the PK50 values. These values have been available in the command line and in the REST API, but they've been somewhat buried within the ADMET Predictor user interface. So now we've exposed them in their own column. I believe when you double click on this column, it opens up a display maybe similar to this one. So it's very convenient to visualize. This is another display in the ADMET Predictor GUI called the Atomic Properties display. I think there are several dozen properties that can be displayed, overlaid on chemical structures, some based on metabolism, some electronic properties. A new property that we added at the request of several clients was a protonation at a user-specified pH. So this is the same compound from the previous slide with the 3 ionizable groups. And here's the display at 2 different pH values defined by the user. So very nice to be able to see the fraction protonated or the percent protonated at different pH values. The equivalent images can also be created using either the command line or the REST API. We've added a convenient way to be able to call an external script from the graphical interface. So you can execute an arbitrary script and integrate the results into the ADMET Predictor spreadsheet. It's compatible with technologies like Python, R, Perl. If you have existing properties in the spreadsheet, like models or descriptors, they can be passed to the script as inputs along with the chemical structure. And we've provided some example scripts in the ADMET Predictor install. So this is kind of a nice convenience feature. Okay, so I alluded to AIDD earlier. We've made several enhancements here. I have just a couple of slides to remind everyone how AIDD works. So this is an iterative approach where you start with one or more seed compounds and then generate analogs of it using an internal database of transform rules. You then evaluate a set of objectives that the user has chosen at the outset. They can include our ADMET models, the HT-PBPK endpoints, 3D similarity to one or more reference structures, models that the user has built using ADMET Modeler, and even callouts to external applications. The population is then pruned by retaining the most optimal compounds, and then these feed back to the generation stage, and this whole process repeats for some number of generations that the user has set. In the end, you're left with a final population that is highly optimized across these objectives. It's quite a versatile tool, and this slide just illustrates a couple of extreme use cases. One is where you very highly constrain the chemistry that AIDD is able to explore. That's done via a very precise scaffold, a Marcouche scaffold in this case. This is useful when you want to, for example, limit the modifications to just one region of the compound. At the other extreme, you maybe have no chemistry constraints at all, but instead you have 3D constraints. So here we've specified one 3D reference structure, and all of the virtual analogs have to be similar to it from both a shape standpoint, a 3D shape, and a 3D pharmacophore profile. So quite a versatile tool, and we've made some enhancements to it. The first one is a new objective that tries to capture novelty. This is based on an ultra-fast search of the analogs against an internal patent scaffold database. So we've constructed that database using two existing compound databases, one being SureChemble, the other PatCID, with many millions of compounds. From these, we have extracted many millions of unique ring system scaffolds, so-called Bemis-Merco scaffolds, and then converted this to a searchable index based on ECFP keys and a technology known as FAIS from Facebook AI. This allows extremely rapid searching. So this is available within AIDD as an objective, but also available as a standalone tool from the ADMET Predictor user interface. Another AIDD objective is synthetic feasibility. So here we trained a model using scores from the retrosynthetic planning software called AI Synth Finder. So the training set included more than 400,000 diverse compounds. This is the final model. This replaces a previous synthetic difficulty score that we had implemented based on the old Peter Ertl paper. It's based on PubChem fragment lookup. The model performance is actually very, very good. It doesn't look as good here because of the density of the 400,000 points, but the RMSE is actually extremely low here. The scores vary, I think, from somewhere around 0 to 2 here, with the higher numbers being more synthesizable. And then some enhancements to the 3D similarity searching. This is relevant both within AIDD, but this tool can also be used to just search a external 3D conformer database, kind of like rocks. So we've added options to adjust the radii and weights of pharmacophore features independently. So there's a little example here where the reference structure that we're using to search the database consists of two things. It's the yellow ligand, but in addition to that, some pharmacophore points. I know we've talked about this, I think, in the last couple of releases. So now you can vary some properties of these pharmacophore features independently. This other ligand is one that was found by using the reference structure in a search against a large 3D conformer database. There's also support for excluded volume features, and there's a new option to save the best alignments for the top n most similar hits, regardless of how similar they are, rather than having to specify a similarity threshold and only saving those with a similarity score above it. That was a bit inconvenient because you don't always know a priori what threshold to use. So we were asked to add this, and we've now added it. Okay, several enhancements to the command line functionality. One of the biggest ones is that the Linux version of the command line now supports image generation. So that really brings the command line version on Linux really on par with the Windows version for the first time. I'll talk a little more about this as we get to the discussion on Linux later on. A couple of new command line workflows. One I've alluded to, which is the HT-PBPK PSA run. And I mentioned that this supports multiple compounds at one time. Another new workflow is to compare experimental to predicted pKa values. And I'm going to just dive into that a little bit more on the next slide. If you're running HT-PBPK from the command line, there's a new argument that lets you append the new dissolved, absorbed, and bioavailable curves to the existing plasma concentration profiles. So this is what a typical HT-PBPK command line run would look like without the plus. So we've had this functionality. You can still generate just the plasma concentration profiles, but with the new plus here, you can append the new curves to it. So we didn't want to break any functionality, but we've extended it now with a new parameter. We've had a workflow for generating atomic property images, and that now supports the new average site protonation. So this is protonation at user-specified pH that we talked about on a previous slide. That's now supported. And then several clients have asked us to provide a way to check license usage from the command line. It's something you can do from the graphical interface, but hasn't been available from the command line. This lets you see, is there a metabolism license currently available, or is someone using it, for example? Yes, just coming back to the topic of pKa matching. So this is sort of what the functionality looks like in the graphical user interface. The relevance here is you can imagine a situation where for a particular compound, there are 3 predicted pKa values, but you only have 2 experimentally measured values. So behind the scenes, there's a matching algorithm to optimally pair the predicted with the experimental pKa. We made extensive use of this functionality, as you can imagine, during the phase a couple years ago when several companies, Bayer and Roche and Genentech, were contributing their experimental pKa to us to be added to our pKa model. Very useful to have this functionality to benchmark how we were doing on the data, but it was inconvenient not to have this functionality be available in the command line, particularly on Linux. So for this release, we have added this functionality there as well. Finally, some enhancements to the REST API. Just like with the Linux version of the command line, Linux version of the API also supports image generation. We have an open API specification, the so-called Swagger file, that we'll be distributing with the release. This can be useful for helping you to write the client code that will then exercise the API. We've made it a little easier to request predicted properties. So rather than having to provide an explicit list of the properties you want, you can either use shortcuts like module names, so PCB for all the PhysChem properties, MET for all the metabolism properties, or you can provide no information at all, in which case you'll just receive all the properties that are authorized by the licenses that you have. So a little more convenient than it was before. And then we've added just a new simple URI that is used to delete all the files on the server that are associated with a particular job. So for example, you might generate a whole bunch of images in a particular job. You then pull those image files from the server, but they do remain on the server for some period of time. They will be automatically deleted after some period, but you can use a command to delete them right away in the interest of saving disk space. Okay, coming to Linux. So I've mentioned now several times support for image generation. This applies to both the command line and the REST API. These are examples of types of images that you can now generate on Linux. One is metabolite prediction. So this kind of display comes directly from our MedChem Designer sketch software, where you get these kind of tree images of metabolites. It's not just SIPs, but also UGTs. So this is now available on Linux. I've mentioned now several times the atomic properties, several dozens of these, like the protonation at a user-specified pH. And then this is from our pKa microstates display, which I think many people are familiar with, showing predicted pKa, all the ionization microstates, and their relative populations. We support both Ubuntu, Red Hat, and their variants. So essentially all flavors of Linux. We'll actually build a predictor on Ubuntu version 20, 22, and 24, as well as Red Hat 8 and 9. We will plan to release separate install packages for each one of these, appropriately named. And then we will have separate binaries that, well, one of which will link against Qt graphics libraries, which will be required for the image generation capabilities. So there'll be an ADMET Predictor and an ADMET Predictor Qt. The Qt version is likely to require a couple of additional dependencies. So if you're not interested in the new feature to produce image files, then we'd recommend using the version that doesn't link Qt, just to simplify the install process. And then finally, we are changing our licensing technology from Flexera to something called Reprise. It's quite similar to Flexera in the way that it operates, but there are a few key benefits. The first is that it eliminates the requirement of setting up a local license server. This can be burdensome for some of our clients. So cloud licensing is an alternative now that clients can choose. Local servers will still be supported. And then second, it eliminates the requirement to exchange host IDs by email, which is extremely inconvenient. There's a technology called Activation Pro that will allow us to send a pre-configured activation key, which will then be converted to a license file automatically. The plan is to kind of upgrade the previous predictor version, which is 12, so that it supports Reprise. And that way, both versions 12 and 13 can be enabled by the same license file. Simplus will, of course, support clients as they make this transition from Flexera to Reprise. And hopefully, it will be a relatively straightforward one. Okay, that is the end of my slide presentation. And I'm going to hand it back over to Tom, I believe, who has one more poll question. And then we'll hopefully, if there's time, do a couple quick demos.
Thanks, David. I'll go ahead and launch that second poll now. So the question is, are you interested in having someone from Simulations Plus follow up with you about ADMET Predictor? And it's a simple yes or no. And I'll give everybody a couple seconds to answer that. All right, and I'll go ahead and end it there. And we can jump into the demo.
Okay, thank you very much, Jasmine. So we've been getting, more and more questions about the use of the API, that was recently introduced. So I thought I would spend just a little bit more time kind of orienting people to how the API works, how you set it up, what its capabilities are. We've gotten in particular some questions about how to run HT-PBPK simulations through the API. It's quite a bit more complicated than ADMET property prediction. So I thought I'd show at least one example involving HT-PBPK. So we'll kind of see how far we get here with the demo. We want to leave some time for questions. So this is showing kind of what the ADMET Predictor install looks like. There's the main executable program. Clicking on this would launch the graphical user interface, but it also powers the command line version of ADMET Predictor. There's a separate file, ADMET Predictor Service, which powers the API. So you would install this, this is assuming you're on Windows, you would install this as a Windows service. I have it running here on this local machine, and at your organization, you would typically designate a single server that all of the users have access to. So that service is running. There are, unlimited number of ways that you can access this API in the sense of, what does your client look like? I mentioned our ADMET Predictor, is one type of client. I like to use one that we also distribute with the ADMET Predictor package because it helps to show all of the back and forth, the queries and responses to kind of help illustrate, how you would set up your own client. So this is included with ADMET Predictor. I think I gave a short demo on this tool in the last release webinar. So I've already set it up to, point to my local machine since that's the one that's running the ADMET Predictor service. And, there's a port number that's involved. So that's all been set up. So I'm going to just load a first example that involves an HT-PBPK simulation. A few things I just wanted to highlight because we get a lot of questions about this. So this is kind of what the original request to the API looks like. So it's HTML. It uses JSON formatting, which is pretty standard. It's not terribly complicated. There's a compound section that has the compounds that you want to run the predictions on, and there's a parameters section. What I particularly wanted to highlight here is how you send data, in particular in vitro experimental data, to the API when you are running an HT-PBPK simulation. We get this question all the time. So in the compound section, in addition to providing an ID value and a smile string for each compound, you can provide any number of additional fields. So these could be experimental data that you have in your database. And they could be named according to how you name them in your database. So here there's a dose value. Let's just call this an experimental solubility, an experimental intrinsic clearance. We'll call it a dog clearance. Some of these values may be missing for some of the compounds. For some of them, you may have an experimental data of type 1, your sort of primary clearance assay, and there's a secondary clearance assay as well. So all kinds of different permutations possible. So the key is that in the parameters section, in addition to some basic information like format is smiles, I've chosen a species, in this case, one of the new ones, dog. The real key here is that you have mapped the experimental data, the names that you have used, that are, let's say, contained in your database. They are mapped to names that ADMET Predictor recognizes. So there's a name for dose, for solubility, and for clearance. These names come from the so-called HIA files that we distribute with ADMET Predictor. So they are what tell ADMET Predictor, what properties to use for each of the key input parameters. If you run HT-PBPK from the command line, then you are probably very familiar with those HIA files, and you edit those files. If you're running command line, that would be the mechanism by which you would tell Predictor that you want to use such and such experimental data in your HT-PBPK simulation. So this is the equivalent way of doing it within the REST API. You'd have a mapping here. There's quite a bit of flexibility in the mapping. So for the solubility, this type of syntax would indicate that you preferentially would like to use your experimental solubility as the input. But if there's a particular compound for which this experimental value is missing, then you would like to fall back to the ADMET predictor model of solubility. There's no limit to how many of these little pipe characters you can insert here. So you can have a very complicated fallback chain here where you use this experimental value preferentially if it's missing some secondary assay followed by a model that you built. And then finally, perhaps the ADMET predictor model. So that's the mechanism. And then similar thing here for clearance. We've supported an option called CP time to generate concentration time profiles. The plus will append the new dissolved, absorbed, bioavailable curves. And then the 0.2 indicates 20% sampling of the time points. This is a option we provided to preserve some bandwidth. So quite a bit of information there. I'll just very quickly run it. I've kind of gone over this before, so I won't spend too much time here. Interaction with the API is a bit complicated in the sense that, there may be multiple jobs being processed by the API at any given time. So you are provided back as a response a job ID, which you then use to repeatedly query the status of the API to determine whether your job is complete. So you ask, what's the status of this particular job? It may be in the queue, it may be running, depending on the load on the server. At some point you get a response saying the job is complete. Here are the properties that were predicted, all the PK endpoints and so on. And here are the values for each of the compounds that you specified, followed by information about the CP time curves. I have an external viewer hooked up. There's a lot of things going on here. I actually have a setting where this information is extracted from the JSON, put on disk as a file. I have a separate viewer that I use for QA purposes just to show that, these are the 4 curves and they look pretty decent despite the 20% sampling. So that's something that you can choose yourself. You're kind of deciding between high quality images and the bandwidth in the back and forth between client and server. I'm looking at my watch here. I'm looking at maybe 10 minutes left until the hour. I had a couple other examples to show in the API, but this is the main one I wanted to show. The next one was the PSA, and the last one was something that we get a lot of interest in, which is how do you predict the predominant ionization state of a compound at a user-specified pH value? So at pH 6, what is the dominant ionization state? So that's something you can do very easily using either the command line or the REST API. The user manual does talk about it at length. So I think with 10 minutes to go, I'm going to wrap it up and let's take some questions.
Thanks, David. I'll jump in now to check if anyone has any questions. For anybody who doesn't know, there is actually a little Q&A box at the bottom of the screen. If you would like to enter some questions, please feel free to do so. We have had one come in during the talk, so please add them while I ask that question. In the AIDD synthetic feasibility feature, do you have the capability to predict possible products if the reactants and reaction conditions are given, such as oxidation, nitration, etc.?
Currently, we do not. I'll let Michael elaborate on this. I wasn't involved in the building of that model, but I think for now, we don't have, the capabilities that the underlying AI Zinth Finder software had. So it's just the raw score. It's really meant, to favor analogs that would be possible to synthesize at this stage. It's not to say that we won't explore having something more complex in the future, but for now, the focus was really on AIDD and trying to bias toward more synthesizable compounds.
Yeah, I really can't add a lot to that. Just repeat what you said. So we're just took the scores out of this AI Zinth Finder. AI Zinth Finder is public, so you could download that program and look at synthesis that, and I think that would help your potentially answer your question there.
Great, thank you. Another is, when can we download the new version of ADMET Predictor 13?
Very good question. I know in the past we've made a Herculean effort oftentimes to have the download be available on the day of the webinar. It's not going to be available today. We're putting just the final touches on the installer package. It's a little bit, different this time because of the switch I mentioned from Flexera to Reprise. So we're still putting the installer together, but it should be available next week.
Great, thank you. Apart from small molecules, any updates on PROTACs and macrocycles, etc.?
You want to take that one, Michael?
No, that's definitely an active research area that we're working at, and trying to incorporate more of those large molecules into our data sets. But there are some larger molecules in this solubility database that we rebuilt, or the one from Avdiv has some larger molecules in it. So that is part of the solubility.
I'll only say that I'll agree with Michael that it's an active area for us. Just this morning, there are messages going back and forth between scientists on this very topic. So definitely a focus.
So a follow-up question to that is, will the newer version also be incorporated into GastroPlus?
As far as the new model predictions, I'm assuming that refers to things like the new solubility model. If that's the case, the answer is yes. I'm not exactly sure when the next version of GastroPlus is coming out, but it will come with the newer ADMET Predictor predictions built in.
Yeah, that's right. So the next version of GastroPlus, I think later in the summer, towards the end of the summer. And what GastroPlus now does is that there's a special ADMET Predictor module, I think, that gets installed even with our installer. And then with GastroPlus, when you import molecules using ADMET Predictor, you can choose which module you want to do or use. So currently it supports ADMET Predictor 11 and 12 in GastroPlus 10.1 or GPX 10.1.
Yeah. So the new option will be ADMET Predictor 13.
Yep. Good question.
Thank you. Going back to the question on PROTACs, etc., I guess one question has come in about ADMET Modeler and building your own models. Is the data that is used to build your own models shared with Simulations Plus or other organizations?
No, that data is yours, and you just can build models with it. We're a little jealous if you've got a lot of PROTAC and other type molecules in your data set. So if you'd be willing to share that, we'd appreciate that. But no, we don't see any models that you build on your own personal environment or work environment.
So is that also allow us to maybe work with our clients to support them in collaborations if they're struggling to build their own models as well?
Sure, yeah. The PBPK collaboration was very successful. We built a very nice model, and the companies shared their data very nicely, and it was a very good collaboration and really improved the model. And we look forward to working with anybody on those aspects.
Great. And then we have time for one last question that's just come in. Does the REST API use encryption?
Good question. Optionally, it does. Yeah, so that's something I didn't get into all the details of how to set up the service, but there's a configuration file with quite a few options that you can set, and several of them are related to TLS encryption. So that's something, I think it's turned off by default, but it's something that you can turn on. And then all the communication back and forth will be encrypted.
Great. Well, I think just aware of the time and we're coming to the end of it. Thank you again, David and Michael, for the webinar and answering the questions. And thank you to everyone who's obviously posted some questions. We're certainly looking forward to the release. And with that, I'll hand back to Jasmine to conclude.
Thanks, Tom. I just wanted to let everybody know that the questions we weren't unable to answer live today, someone from our BD team will reach out to you. I put a couple links in the chat just to invite you to visit our website to learn more about ADMET Predictor. You can also follow us on social media. This webinar has been recorded for playback and will be available on our website and YouTube channel. This concludes our webinar for today. Thank you, everyone.
Thank you.
Hi, everyone. Thanks for attending.
Thank you, everyone.